Grade 12 Physics, Light Note number 8, Maxwell's Equations. Maxwell was a theoretical physicist in the 1800s who derived 4 mathematical equations that could describe all of electromagnetism. We're going to look at those 4 equations here. The first one he called Gauss's law. Gauss's law basically means the amount of electric field lines that pass through a surface is proportional to the amount of charge. So all this really means is that if we draw a charge, the more field lines that are coming from it, this means the more intense that charge is. And that's described through that equation above. The second law he called Gauss's law for magnetism. This is a law for magnetism. Really here, if we draw some sort of a volume, the amount of magnetic field lines leaving a volume of space will be equal to the field lines entering that volume of space. This is the central law behind showing that there's no possible way that magnets can be a monopole, meaning when you split a magnet, we don't get a north and south, we get 2 smaller magnets. The third one he called Faraday's law of induction. This means a changing magnetic field will induce a changing electric field. So here, this is how we can generate electricity. If we move a magnet, which has a magnetic field around it, if we move it near a current carrying wire, it will actually induce a current through that wire. The fourth equation he called the Ampere-Maxwell law. This is sort of a reverse equation from that third one. This one states that a changing electric field will induce a changing magnetic field. This is one of the central equations that explain how electromagnetic radiation can exist. In electromagnetic radiation, we have an electric field that grows and shrinks, grows and shrinks, grows and shrinks, and this induces a magnetic field that's able to grow and shrink, grow and shrink, grow and shrink proportionally. So when all this was derived mathematically, usually in physics, experimentalist physicists like to try and prove the law is incorrect. Heinrich Hertz was a German physicist. He was teaching a first-year physics class in Germany, and he tried to verify Maxwell's laws. He set up an apparatus, a circular current on one side of his classroom, and he sent some electricity through it. The electricity would make a little spark. But because he had a changing electric field in that apparatus, it induced a changing magnetic field and sent out electromagnetic radiation. That radiation went across the classroom and it rubbed up against a similar receiving apparatus on the other side. When that radiation went past, it induced a current in the receiver, therefore making it spark. So in the initial apparatus, he would make that spark. The students would look across the classroom. They would see the other one spark as well, even though it wasn't hooked up to electricity. So this was neat because Maxwell showed that if you have a changing electric field, it would induce a changing magnetic field, therefore creating that electromagnetic radiation. The students asked him, what is it good for? Hertz responded, well, nothing, I guess. But back in the 1850s, they didn't understand how the Industrial Revolution and our technology revolution would use this to invent a whole bunch of things we depend on today, like cell phones, walkie-talkies, anything wireless.